We showed that a single integral can be represented as a double integral with an integrand of 1. Consider the problem that we looked at earlier. I have some nebulous region, but since I can integrate it with respect to x or with respect to y with the single integral, my double integral could also be with respect to x or with respect to y first. So we generically say the integral over the region in the xy plane, that would be this region here, integrated with respect dA, meaning dA is either dy dx or dx dy. You would choose it based on whichever one was easier to set up. Just like in Calculus 1, you'd decide whether you wanted to integrate with respect to x or with respect to y. Now imagine a situation where this is the region in the xy plane, but it actually has a height of 1, in which case the area would equal the volume because I'd be multiplying the area by 1. So now imagine that this here represents the height above the region in the xy plane. So let's come up with a different picture now. So suppose now I have something that looks like this. I have some surface, z is a function of x and y, and I'm interested in finding the volume below this surface. So let's say as it projects down into the xy plane, I have some region here. Oh, let's call it rxy. So the shadow this makes straight down, and I'm interested in setting up a situation where I find this volume. Well, if I only wanted to find this area, we would have said, let's set it up this way, dA. But now that I want to find the volume, my height isn't 1, but f of x, y, z. Or excuse me, f of x, y. So I would perform this integration, and that would give me the volume. Now we know in Calculus 1, the first introduction to the derivative was to find the slope of a tangent line, but we realized later a derivative could be used for many things. Our first introduction to an integral was finding area under a curve, but we know that integration can be many different things. It can be used for centers of mass as well as other things. Volume is the first introduction of a double integral, but it's not the only. So I want to consider, what if I simply wanted to evaluate a double integral? Let's say a double integral in the form, how about 2x plus 2y dy dx integrated 1 to 3 here, x to 2x here. Now the way we look at this problem is it's an integral within an integral. So this is one problem all by itself right here. I'm going to integrate this and evaluate this. And as a result of this integration, I will get completely a function of x. Then when I perform that integration with respect to x, I will get a scalar. So as we walk through this problem, we do the inside first. Now I'm integrating with respect to y. If I was doing a partial derivative with respect to y, we treat x as a constant. So we do the same thing with integration. If I said integrate a constant with respect to y, we would get 2xy. If I said integrate 2y with respect to y, we'd get y squared. And now I'm going to evaluate that from x to 2x. Now the question is, where do I substitute those in? Well, I was integrating with respect to y, so I'm going to replace the y with these values here. And then when I'm done, I integrate all of that with respect to x. So what I get at this point in the way, this is the integral from 1 to 3 of 2x plus 2x squared. That's the first term. Minus 2xx plus x squared. That's the second term, all integrated with respect to x. If I simplify this quantity, it will simplify to 5x squared dx, and the rest of the problem is simple. This is just a Calc 1 integration now. So I'd have 5/3 x cubed from 1 to 3, which would be 130 thirds. So this is how we evaluate a double integral. Now I'm going to post several examples on Canvas, so look for them. But in the meantime, now you have the start for the multiple integration that we will finish the exam 2 material with.